All right. So, couple of just general questions. Okay. When we refer to a number referred to as an octet, what do you think that would mean? What number? It is 8. Okay. So, uh, because yeah, you could say 2 is a dual, 3 is a trio, 4 is it is, but would that be a quartet then? Then a quintet, then it would be a heptet for, no, I don't know if you, a special group for 6 people, but by the time you get up to 8, you would prefer that would be an octet because when you look at your stop sign, yes, it's an octagon, so it has 8 sides. So when we're referring to an octet, we're referring to the number 8. So what 2 groups on the periodic table would add up to 8? It can't be the F block because you're already past 8. That's 14. It can't be the D block because you're already past 8 because that's 10. So when you put the S block and the P block together, if they're both full, you'd get the number 8. Okay? So what are some concepts that we maybe talked about that's on this table that would really help you out? Like yesterday, we said the element, we did like calcium, for instance. What column is calcium in? And I wouldn't expect you to know without looking. It's in the 2nd column. So, if that is the case, do we see the element calcium up here? No. These 2 elements are what and what? It doesn't tell you, but remember, it's the atomic number that identifies it. So who's element 19? Okay. And who is element number 17? Chlorine. So you're correct in both cases. Now, notice that potassium is right next door to who? To calcium. We said it was in column 2. But since potassium is in column 1, how many electrons are in its outer energy level? There's only 1. So if we added 1 more electron like what we did yesterday, we would have calcium, and that would be in column 2. So it wouldn't have 1 valence electron, it would have 2. So a valence electron or electrons is the total number of those in its outer energy level. That's what valence electrons are. Okay? Yes. And you can do that for any element from 1 to 8. But you can't do that for D block elements because there's 10 columns. You can't do that for F block elements because there are how many columns in the F block? 14. So, what I'd like you to do is pick a number between 13 and 18. 17. That's what we have here. How many valence electrons does chlorine have then? It's got 7. So if we say 7, which we did, we can identify chlorine is in which column? The 7th. So do we see how we identified valence electrons with its column? Does that make sense? Okay? So potassium being in column 1 is a metal. It would be considered as a what type of metal, though? Not non-ferrous, but a vocab term. An alkali metal, okay? Because when you look at any type of batteries, whether they're rechargeable or not, there's probably what metal in here? And yeah, it's an alkali metal, but it's in column 1. It's lithium. That's why they call them lithium-ion batteries. And that's why you call them alkali batteries, because it has an element from column 1 in here. Okay? So column 2 is also a metal, but it's a little more complex, you could say. or a little bigger. So it's not alkali, but rather alkaline earth metal. Okay? The most stable elements on the periodic table are who? Elements in column what, do you think? In column 8. Because those are the noble gases. Elements in column 8 are known as the noble gases. So, I want to get this turned on or else it's going to go through the sleep mode and shut off. We'll come back to this on the board in just a moment. Okay, so this is where we left off with yesterday. So, as we look at this, again, the number of protons tell you which element you have, referred to as which number? The atomic number. How is the atomic number different than the mass number or atomic mass? What is the mass number or atomic mass of any element? Right, when you add them together. So when we had, for instance, element potassium up here, we said P equals 19 because there's 19 protons. Then how did we get 20 neutrons then? 39. So 19 from 39 gives you 20. So calculating neutrons. Middle, are we good with that? Okay. Left outside. Okay. To get the number of neutrons, okay? For instance, is what we see here. Maybe make it a little bigger. Okay, so if we're dealing with potassium here, element number 19 and 39. We've got 19 protons in the nucleus. We would agree with that. The protons and neutrons together is 39. So to get the number of neutrons, you would subtract, remember, protons plus neutrons equals atomic mass. Okay? This is 19 plus n equals 39. So how do you get n by itself? You subtract the two. And that's true for any element on the table. So when you take 19 from 39, you get what number? 20. And that's why the 20 is written in there. Okay, like I said, anything from element 1 all the way up to 118. Okay. So, now, some of these, the number of neutrons can vary. Carbon is the best example of that. So carbon has atomic number what? Atomic number 6, an atomic mass of 12, so it has 6 neutrons. But carbon can also have, rather than having 6 neutrons, it can also have 8. So that's how we get carbon 14. And we can illustrate why that is here in just a moment. So an isotope, you're referring to any element, even chlorine. Chlorine can have still 17 protons. A stable form, or neutral, would have, 18 neutrons, but it could also have 19 neutrons, 20 neutrons. That means it's an isotope because it has the same number of protons, but different numbers of neutrons. That's what an isotope is. And carbon is the most common. Oops, I'm sorry, I didn't continue on. I said middle was good, so left outside, are we good? Okay. Right middle. Right outside. Right outside. Okay? And left middle. this information that wants it. Yes. Okay. All right. So, organizing elements. We've been spending some time with this, okay? No surprise here. They're arranged in increasing atomic numbers. That's why you see 1, 2, all the way up to there to 118. There are some exceptions in some areas where it's not arranged in increasing atomic mass, but rather this increasing atomic number. Okay? And again, what this is saying is how the periodic table gets its name. There's certainly a repeating pattern that we see here, like the what does it say, number of the moons that go through a monthly cycle, of course days in a week, the months in a year, all those continually repeat themselves. But when we look at this, Mendeleev or Mendeleev, I can't remember which way it's pronounced, okay, actually arranged this first table in increasing atomic mass, which is fairly close or fairly accurate, but it's not quite correct. There, like I said, there's some certain exceptions in there where it actually decreases in atomic mass. I think iodine is the most common one, because if you look at that, we find element 53, okay? Tellurium, element 52, has an atomic mass of 127. Iodine has an atomic mass of 126, okay? So by this standard, it would be out of place, but the increasing atomic number places it in the correct order then. I want to do one more, take a brief look at the board, and then we'll continue with hunting the elements. Seeing those different types of examples, like what that alloy is, copper and tin making brass, when you see examples of that, is that helping this supplement the material, or is it just totally boring? We're asking for input. I'm asking, get this wrapped up so we can continue that, or you would be dreading getting back to that video. We want to see the video. Yeah. Okay. Asked and answered. Okay. So again, I don't know. I want to say this was somewhere around 1910s, 1920s, somewhere in there. So arranging these was actually pretty significant, because can you see any gas? No, you can't. You can't see hydrogen. You can't see helium. You can't see any of those. You might say, well, we can see neon. Well, that's only true if it's in a vacuum and you got what running through that? Electricity. Right. Okay? So in certain cases, some of these physical properties and chemical properties of these gases actually make them quite dangerous. Okay? For instance, we call hydrogen sulfide a very dangerous gas. But you wouldn't probably have heard that, but rather sewer gas. Okay? We associate the smell of a sewer being something totally terrible. Well, yes, that's true. But hydrogen sulfide is something that you can't see it, you can't smell it, just like carbon monoxide. You can't see it, you can't smell it, but you can only maybe distinguish what it's doing to your body. And one of the things that happens is in a heat exchanger in a furnace, let's say there's a crack in there, or as that furnace is running, we know that as things burn, what's given off into the atmosphere? Carbon what? Carbon dioxide. But in certain cases, people unfortunately succumb to fumes of not carbon dioxide, but rather carbon monoxide. There again, It's a gas that you can't see or smell or anything to that effect. So, well, how would you be able to arrange an entire periodic table for things that you can't see or smell? There's a simple way that they had done that. However, they could isolate the element hydrogen. If you put that on a scale, and if something is 8 times the mass of hydrogen, means it's got 8 protons. So that would be which gas then? Oxygen. That's right. So it has 8 times the mass. Well, then you might say, well, it's got an atomic mass of 16. Well, that's true, but it has those 8 more protons. And I think they explain that here in this video. And that's why I think it's so important having that to supplement this material. Because for those of you who are sitting here saying, yes, I understand this. Yes, I understand this. When we get to this on Monday and we hand it out and we say, I don't have a clue of what we're doing, you are not doing yourself any favors. Okay? Because there's nothing worse than being, let's say, in last place and trying to play catch up. Sometimes, has anyone been stuck in that in a relay race? 4x1, well, that's not so bad, but let's say the 4x8. It's a 2-mile race. Everybody's running 800 meters. Has anyone ever received the baton and you're in last place and have to run 2 laps? It's not very fun, is it? Did you catch anybody? So, see, this is where you can say, but this is where you can say it was somebody else's fault, and that would be true. Because you were given the baton already in last place. Okay. So, we continue. See, there's always a simple solution to that. Run how? You've heard this before. Run like you're late for science. How simple can it be? Whether it's track, cross country, or even football. I say that to some of the individuals. The end zone is the doorway to the science class. Zoom! There you go. What was that streak? That was Easton running across the football field, or Ben, or maybe Sawyer. I don't know. One of the individuals. Okay. So, last one. Okay. So what we see happening, we illustrated there's a problem with arranging these in increasing atomic mass. You have to put them in the proper order by increasing atomic numbers. So in the 1930s, maybe a scientist by the name of Moseley put them corrections in place, and that is considered as the modern periodic table. Even though we said this has a copyright of 1991 on this west wall, it's still considered as a modern periodic table. Darn it. Hopefully you didn't crack our phone. Does everyone have this information that wants it? Okay. not even dancing. That'd really be hilarious. Do a TikTok? Something like this? Okay. All right. Now, does everyone have this information that wants it? Okay. So, one of the things, again, we've said this before, the more you know, the less you have to learn. You can't really argue with that statement, can you? Okay? Whether it's learning something like this or even some of these bus routes that we drive. Well, not we, that someone drives. Okay? The more you know about where someone lives, it's easier to navigate where you have to go. So, the more, this is for those of you going into science in college. Who might that be? Okay? Just think, if you're going to be a nurse, a doctor, a pharmacist, any one of those, when you actually have a good understanding of these organic reactions, you're already, hopefully, way ahead of other people. And what we mean by that, again, the more that you know, the less you have to take time to learn in college, because you already know that material. Okay? So that's why this has some hidden chemical properties. It's way too advanced to talk to you individuals, but for those of you going into that, if you take time to learn and understand this, you're going to be way further ahead than other people at the same level. Okay. So, with this, we can, again, make some of these predictions. Again, noble gases are in which column? So they are very, very stable. So you can make a correlation that elements that have 8 valence electrons, whether they are theirs or not, will make them more stable. Okay, so what we mean by that is if we take this chlorine over here, and I'm going to write it from right to left instead. Okay, so element 17, 1s2, 2s2, 2p6, 3s2, but there again, the P block only for chlorine is in which column in the P block? The 5th one. Now, when we put that entire period together, we get 7. Notice, chlorine is in which column? 7th. It's in which period? How many energy levels do we have? Do we see some of these periodic functions showing up over and over and over again? Okay? So now, if we have potassium there, or excuse me, chlorine there, and now we're going to put potassium, 19, okay? Tell me, 1s2, what comes next? 2s2, 2p6, 3s2, 3p6. Do we go to the 3D? No, because potassium is in which period? Potassium is in which period? Periods are horizontal. 4th. It's in the 4th period. Okay? So, since it's in the 4th period, that says we need 4 energy levels. Now, what column is it in? Our vertical. So that means it has how many valence electrons then? 1. Chlorine has how many valence electrons? 7. Remember, valence electrons are those in the outer what? Energy level. So, column 1, 1 valence electron. Column 7, 7 valence electrons. Now, we said the noble gases are very stable. Why? Because they have how many? 8. Now, notice neither one of these have 8. This one's got 1, this one's got 7. So what this will do is potassium is a very, very unstable element, just like all of those in column 1. They've got this one electron that they really want to get rid of. Because remember, we said on Monday, you go into the movies, ladies, we said, okay, the guy who takes you there, maybe pays for the ticket, the popcorn, the pop, whichever. Because guys, you're just so nice in here. All right. So what happens, how can this have or obtain, if it has 7 valence, where do you suppose you could get one more? From a metal. Specifically, which one? The one that's right here, which is what? Which is a metal. So what happens is this electron then is donated or is transferred over to here. Now this is now gone because it transferred itself over to the chlorine. Now, how many valence electrons are now in here, numbers and letters? 8. How many, even though this is empty, this is now the outer energy level. How many electrons are there? Now both of these are very stable now. It makes what we call potassium chloride. Okay? Well, it's chlorine, but when it ionizes, it's called chloride. Okay, last thing. How many positive charges does potassium have? 19. How many, add them numbers together, get negative charges? 18. So if we add, when you add 19 plus a negative 18, you get what? Plus 1. Have we changed the number of protons in here? No. There's 17. Numbers and letters added together gives you what? What happens when you add them two numbers together? You get negative 1. What does it say in your upper right-hand corner of chlorine? Negative 1. That's where it comes from because it gained another electron. What does it say in potassium's box? This is why, because it gave that electron away. Okay. We will continue with this video now. Again, if we're not, this is going to be the next thing that we talk about, especially with configurations. These are what we call Bohr models. If we are struggling with these and you're saying, yes, I understand this, when you really don't, it's kind of like having race car tires. It's like having race car tires on a frozen lake. How are you going to get off that lake? You're saying no. You are correct. Not that everyone knows, I'm not big into racing either, but what's true about the tread on race car tires? There is none. They grip the road. They can't grip ice. So where are you, if you're in the middle of that frozen lake, which it's safe to be on, and you've got race car tires, you're just going to spin and you're not going to go anywhere. So that's what it will be like for yourselves. I don't say that to be mean. I'm just telling you that you're just making it more difficult on yourselves. And that's a personal choice that you may be possibly making. So take initiative, please, and ask questions. All right. So we continue with hunting the elements. And hopefully, I think this has a problem picking up the sound. We'll see if it can continue to do so. Okay, don't forget, we have some vocab terms that are due tomorrow. So get them done, and then we'll have a paper for you to work on shortly after this week, at the end of this week.